In this video, we'll look at a couple more examples of problems that involve differential equations in different ways from what we saw before. There exists a relationship between two variables, x and y. Nothing fancy here, they don't stand for anything, just two variables, such that the rate of change of y in respect to x is double the ratio of x to y. So we've translated the problem. dy dx equals 2x over y. Then we want to write an equation. Notice how they're not immediately asking us to solve this. So while your first instinct might have been, oh, let's separate the variables and integrate both sides, read the question first. We don't actually get asked that right away. Write an equation for the line tangent to the graph of f at 1, -1. And remember, when we're talking about writing equation of a line tangent to the graph, think point slope form. That means we want y minus f of a, or in this case that a happens to be 1 because that's the x value, equals m, the slope, which is the derivative at 1, times x minus 1. This is point slope form. Y minus y1 equals m times x minus x1. Well, they already told us that f of 1 is -1, so we want y minus -1 equals some derivative, I'm going to call it f prime of 1 for now, times x minus 1. Well, that just means we need to find the derivative when x is 1. Well, if dy dx, and I should say, maybe using function notation here isn't correct. I don't really know that this is a function. In fact, it doesn't tell me that it is, so I shouldn't assume that it is. So maybe I shouldn't use the notation f prime of 1. Maybe I should have called it dy dx evaluated at x equals 1, y equals -1. But you can see why I chose to go with the simpler version. But now I'm going to say it the long way, because I need to know what that derivative is so I can fill in the slope. Well, it's 2x over y, so it's 2 times 1 over -1, which is -2. So my equation is y plus 1 equals -2 times x minus 1. And that's all I need. Part B asks me to approximate f of 1.1. Well, what that would mean is when x is 1.1, use the tangent line to approximate what y would be. Y plus 1 equals -2 times 1.1 minus 1. So that's y equals -2 times 0.1 is -0.2 plus 1, which is 0.8. And that would be not exactly what y is when x is 1.1, but it's our approximation based on the tangent line. And now in part C, it did ask us to find the particular solution to the differential equation. So now we are going to do what we expected, which is solve this differential equation. And remember, the 3 steps we need to think about are separate, integrate, solve. So let's move the y over, y dy, move the dx over. And the one thing you should notice is, unlike most of the other examples we've seen so far, there is no denominator here. That's not dy over y. So when we do integrate, we're not going to see the ln's that we've been seeing a lot of. Some of you might be happy about that. Y squared over 2 equals x squared. I don't need the over 2 plus c. And then using the initial condition that f of 1 equals -1, we can plug that in here. -1 squared over 2 equals 1 squared plus c. So 1/2 equals 1 plus c. c equals -1/2. So we can write the equation using our value for c. Y squared over 2 equals x squared, minus 1/2. And that's it. That's all you need to do. You don't need to get y by itself here. In fact, you really can't get y by itself here without using a plus or minus symbol, which we'd rather not do. It didn't say that you had to write your equation y equals f or something like we saw in other examples. So it is okay if you leave your solutions not necessarily y in terms of x alone, not as a function, but as a implicit relationship like we have here. If the problem specifically asks you for it, like we saw in the last example, they asked specifically to find the particular solution y equals b of t, that would mean we needed to get the b by itself. And that's the difference there. Okay, we'll take a look at another example, which is not going to get us very far. dy dx is 2x minus y. What's different here is we're seeing subtraction, and we haven't seen that before. And that makes a huge, huge, huge difference. Our first job is to separate, but we can't. You can't pull apart the x and the y if they are, there's addition or subtraction separating them. You might be saying, oh, why don't I just add the y to the other side? And sure, you can add the y to the other side. But that doesn't help, because if you were to try to integrate both sides here, which you'd be allowed to do, you just have no way of integrating this. The integral of y without a dy doesn't mean anything. So we'd kind of be stuck there. So this is what we would call a non-separable differential equation. We can't use the method that we've been using in order to solve it, which means there's nothing we can do. We will learn next class about some things we can do, but none of them are going to be solve the differential equation. We can't. We won't be able to. But that doesn't mean we can't be asked things about it. So one particular solution of this equation has a local minimum at x equals ln of 1.5. So, and then the question asks, what is the y value at the minimum? So what you need to do is be able to translate this in your head. And this is where all the things we do throughout the year, they all tie together. When we hear that the equation has a local minimum, think for a second, what are some things that means to us? Hopefully you came up with the idea we're looking for. At a local minimum, we know for sure that the derivative is 0. Which means, and they're telling us it happens when x equals ln of 1.5. So 2x minus y equals 0 when x is ln of 1.5. So 2 times the ln of 1.5 minus y equals 0, which means that y must equal 2 times the ln of 1.5. And that's all they're asking us for. That answers the question. And so the moral of the story here is that not every question about differential equations is going to eventually ask us to solve it using the separable differential equations. We don't always have to separate, integrate, and solve. Read the questions carefully and be able to tie in things that we know from earlier in the year, and you'll be able to figure out what to do.